And the second setup is actually an HVAC. So we're going to use, again, a 3D simulation. Single phase, we're going to have internal simulation, so we're not going to use the default setups. We're going to use the segregated energy. Okay, it's actually our thermal solver, so we're going to use that in this case. What else? We almost done. Okay, we're going to set a 300 Kelvin initial temperature field, some gravity. Okay, and we leave default settings. The only thing we change is the equation of state to Boost-Nesk. So we're going to take into account the variation of density with temperature. And then we import all our geometries. Okay. On the contrary of the previous demo, we're going to have to import a few of those. Okay, so we're going to have, all of those geometries. We're actually importing the domain which defines our computational study. So in this case, it's this box, which are the walls of our room. But we're also importing the furniture, okay, the air conditioning geometry, and then we have two additional ones, which I'm going to show you right now. So that one is our outlet. We're actually setting one surface as an outlet in the simulation, otherwise our mass flow will keep increasing. And the second one is this additional geometry, which we are not going to use for the simulation, and that's why we're going to set it to disable. But it's going to be an auxiliary geometry to do our stream tracing and post-processing. Okay, so let's switch this one off. Okay, so now let's set up a few boundary conditions. Well, the easiest one are the outlets. It's going to be clear an outlet. So instead of wall, we're going to set to outlet pressure. Okay, the most complicated one is the air conditioning. Well, basically it's a whole body, so I want to select only the top surface to set my velocity condition. And I can easily do that in XFlow by selecting the phase filter, select my surface of interest, and then apply boundary conditions to phases. Now I do have two split surfaces, okay, and I'm gonna label that to inlet. I'm gonna set an inlet velocity of 4 meters per second on the y-axis, and I want my inlet velocity to be cooler, so I'm gonna set a temperature of 288 degrees. Okay, so we have 300 K in the room and a cooler flow coming in. Okay, the rest is actually left untouched, so we have walls and adiabatic for all of our furniture and walls. Okay, and we just need to set a few discretization parameters. So again, our resolve scale is going to be of the order of 0.2 meters. And again, I'm going to use adaptive refinement. Okay, so we're going to see that the refinement basically adapts with the flow. So we'll try to track where the high velocity field is going to be. Okay, I'm going to leave everything but to 0.1, but the air conditioning. So that's 0.05 and 0.05. Okay, and then I'm going to change the wake resolution as well to 0.05. So I'm going to have the same resolution on the wake and on the surfaces. Okay, and nothing else. That's my HVAC simulation. And probably I want a lower resolution for my frame frequency. Okay, so that's it. I can again save this one and set that to HVAC and hit the run button. Okay, is as simple as that, as you can see. So again, we're generating our discretization, and then the solver will start in a few seconds. Once again, instead of waiting for the actual solution, which is simulating in my machine, I'll just load a few frames of our post-processing and probably show you something I did not show on the previous case. And in particular, for example, we can see that we can place sensors in the room, so places where we can then measure temperature, and that's our evolution of the temperature over time. So it starts with the 300 degrees that we had, but then it goes down. Okay, and I'm going to do a plot of temperature in the room, so we can see if we close that to the air conditioning. well, that there is a cold stream coming from the air conditioning, hitting the roof or the ceiling, and then it starts cooling down the entire room. We can see the velocity field and how there is an increase in velocity near the outlet that's basically sucking the air out. Okay, but then we can start having a few traces. So in this case, what I'm doing is again having a few traces on the additional geometries. They are advected on the flow field, so you can see how they're transported by the velocity field. Okay, in this case we have a constant flux of particles coming out every second, but you can see the effect of the air conditioning. Okay, probably last visualization tool before we close down for questioning. That's a volumetric rendering of temperature. So what we're trying to plot here is how the temperature, the cold temperature from the air conditioner is actually entering the domain and affecting the solution. So you can see that, well, we start having the entire domain is around 300. So now we have cool temperature coming in, and we can see the evolution. So if we advance on time during our simulation, we can see how that cold air is spread around the room. Okay, and we can see the effects at the same time on the sensor here. So we're cooling down the specific part of the room.